All right, let's talk about a really fascinating paradox that's shaking up the world of AI right now. For years, the mantra has been bigger is better, right? Just build a bigger model, throw more data at it. But what if that's not the whole story? What if a tiny AI, we're talking smaller than a lot of apps on your phone, could actually outthink the biggest, baddest models out there?
I know, it sounds kind of crazy, doesn't it? You've got these tiny models with just millions of parameters, and you can think of parameters as the little neurons or tuning knobs in an AI's brain. And they're going up against absolute giants with hundreds of billions, sometimes even trillions of parameters. It's the ultimate David versus Goliath showdown, and it's happening right now on the cutting edge of AI research. So can it really be done?
Okay, so here's how we're going to break this all down. First, we'll look at the kinds of puzzles that make even the biggest AIs sweat. Then we'll check out an interesting but, well, flawed first attempt to solve this called HRM. After that, we get to the star of the show, the less is more idea behind the tiny recursive model, or TRM. We'll get into how it simplifies the math, look at the absolutely jaw-dropping results, and then wrap up by asking, what does this all mean for the future of AI? Let's get right into it.
All right, Section 1, AI's toughest puzzles, where the giants stumble. So let's set the stage here. We all think of these large language models, LLMs, as these, incredible digital brains, almost like intellectual superheroes. But it turns out there are certain types of really tough reasoning puzzles where these giants just fall flat on their face.
So, the big question is, why? Why do they struggle so much? Well, it really boils down to how they think. An LLM generates its answers one little piece at a time. It's called a token, but you can just think of it like it's writing a story one single word at a time. Now, for a conversation, that works great. But for something like a super hard Sudoku puzzle, if it puts just one wrong number in one box early on, poof, the whole solution is completely toast. It's a single point of failure. Now, they've got workarounds, right? They try to use these complex techniques like chain of thought, where the model literally tries to talk itself through the problem. But that can be super slow, super expensive, and honestly, pretty brittle. If it makes one logical misstep in that chain, the whole thing just collapses. And the proof is in the pudding. When you test them on these really tough benchmarks like ArcAGI or hard Sudoku, they just don't make the grade. And this weakness, this Achilles heel, it created a huge opportunity. The community started to realize, hey, maybe just scaling up, just building bigger and bigger models isn't going to solve these kinds of problems. What was really needed was a totally different way of thinking, a smarter approach, something that wasn't about sheer scale, but about clever design.
Okay, on to our next chapter. HRM, a complex contender. This was an innovative but flawed first attempt. And this brings us to a really fascinating model called the hierarchical reasoning model, or HRM. You've got to give them credit, it was a super creative first swing at this problem. The whole idea was actually inspired by the human brain, how we seem to process things at different speeds on different levels.
Now, the design of HRM was, well, it was a lot. It wasn't simple. It had two separate networks working together. There was a low-level network, let's call it FL, that was meant to churn away really fast. And then there was a high-level network, FH, that worked more slowly, kind of supervising things. The idea was that the model would keep looping, or recursing, to slowly improve its answer over time. But here's the tricky part. To make all of this computationally possible, to not just blow up your computer's memory, they had to use a pretty heavy-duty mathematical shortcut. It's based on something called the Implicit Function Theorem, or IFT. Basically, instead of calculating the perfect way to learn from its mistakes, it approximated it. A clever idea, but a shortcut nonetheless.
And this is where we find the crack in the foundation. That fancy mathematical shortcut, the IFT, the thing that makes the whole model work efficiently. It all depends on one crucial assumption. The assumption is that the model's internal thinking will eventually stabilize and settle down into what mathematicians call a fixed point. But here's the kicker, and this is a direct quote from the analysis. A fixed point is unlikely to be reached when the theorem is actually applied. Oof. So in practice, the very mathematical justification for the model's learning process, it's shaky. It probably doesn't hold up.
So you have this really clever idea, right? HRM was an awesome attempt, and it did beat the big LLMs on these puzzles. But it was also super complicated, and as we just saw, maybe built on some shaky mathematical ground. And that's what leads to the million-dollar question. Could it be simpler? Could we get the same results or maybe even better ones by just simplifying everything?
All right, here we go. Section 3, TRM, the less is more idea. Introducing the tiny recursive model,
And the answer to that question is a huge, emphatic yes. This is where our hero, the tiny recursive model, or TRM, steps onto the stage. The whole philosophy is right there in the name. Less is more. It takes that brilliant central idea from HRM, the recursive reasoning, but just throws all the complicated baggage right out the window.
And now we get to Section 4, Simplifying the Math. This is all about how TRM streamlines reasoning. So how on earth did they pull this off? This, right here, is the real magic of TRM. It's not just that they made the model's architecture simpler, they went deeper. They completely streamlined the underlying math of how the model thinks and learns.
Just look at this comparison. It's a radical simplification. Where HRM needed two separate networks, TRM says, nope, we just need one single tiny network. Where HRM was leaning on that shaky implicit function theorem, TRM just goes, you know what? We'll just do the work. We'll use direct backpropagation. No fancy theorems needed. It replaces these complex, abstract, latent variables from HRM with two super intuitive concepts, an answer and a scratch pad. We'll get to those in a second. And get this, it even makes the training process more efficient. It's just a beautiful example of simplification at every single level.
Okay, so let's talk about those two new variables, y and z. It's so much more intuitive. Think of it like you're doing a math problem. Y is your final answer on the page. It's the model's best guess at the solution at any given moment. Z is your scratch pad. It's the side of the paper where you do all your messy work, where you try things out, erase them, and figure out the steps. So the model uses its scratch pad, Z, to think, and then it uses that thinking to update its answer, Y. It's just a loop. Think on the scratch pad, update the answer. Simple as that.
And this gets to the absolute heart of the matter. This is how TRM solves that big math problem from HRM. Instead of taking a shortcut with a theorem that might not even apply, TRM just does the work. It takes the honest route. It uses backpropagation, which is the standard, time-tested way all neural networks learn, and applies it through the entire recursive thinking process. There are no approximations, no shaky assumptions. It's just direct, honest computation. And, as we're about to see, it is way, way more effective.
But wait, there's more. The smart simplifications just kept coming. For example, they tested networks with 4 layers and 2 layers. And guess what? The 2-layer one actually worked better. Why? Because it was less likely to overfit. That's the classic problem where a model just memorizes the answers instead of learning how to solve the problem. They also proved, yep, one single network can totally handle both the scratch pad thinking and the answer refinement. And for tasks like Sudoku, where the input is always the same size, they even got rid of the super famous self-attention mechanism and replaced it with a simpler setup. To top it all off, they added a little trick called an exponential moving average to help stabilize the learning process and stop the model from forgetting what it just learned. Every single decision was about making it leaner, meaner, and more effective. Okay, Section 5, Tiny Model, Giant Results. This is the showdown. So we've got this beautiful, simple, elegant model, but the big question remains, does it actually work? Is it any good? Well, this is the moment of truth. It's time to pit our tiny model against the giants. Okay, just look at these numbers for the Sudoku Extreme benchmark. This is insane. You have a massive LLM with 671 billion parameters. Its accuracy? 0. A flat 0. Can't solve them. Then you have HRM, the more complex predecessor, with 27 million parameters. It gets a pretty decent 55%. Now, look at our TRM. With only 5 million parameters, a tiny fraction of the others, it scores an absolutely staggering 87.4% accuracy. This isn't just better. This is a complete game changer. It's a massive, massive leap forward with a model that's practically microscopic in comparison. And it's not a fluke. The story is exactly the same on the ARC-AGI benchmark, which is this really tough test of abstract human-like reasoning. You can see it right here on the chart. TRM comes out on top again. It beats the big LLM. It beats HRM. It is consistently and without a doubt punching way, way above its weight. I want you to really let this next number sink in. 0.01%. That's it. TRM is achieving these world-class, state-of-the-art results using less than 0.01% of the compute, of the parameters, of its giant competitors. If this isn't the ultimate proof that the answer isn't always more brute force, I don't know what is. The solution is a smarter design.
All right, final section. The future of AI. What does less is more mean for tomorrow? Because this really brings us to the big picture, right? This isn't just about one clever little model.
This is a result that could fundamentally change how we approach building AI. So what are the big takeaways here? What's the so what?
Well, the takeaways are pretty profound, if you ask me. First and foremost, smart architecture can absolutely demolish brute force scale. It's not just about size. Second, this recursive reasoning idea, this loop of thinking on a scratch pad and then updating your answer, is an unbelievably powerful and parameter-efficient tool. We also learned that on some problems, especially where you don't have a ton of data, small networks are actually better because they don't fall into that overfitting trap. But maybe the biggest lesson of all is that progress in AI is not a straight line. It's not just about building bigger and bigger models forever. There are other paths, smarter, more elegant paths to creating intelligence.
And that really leaves us with one final, fascinating question to chew on. For years, the entire AI world has been dominated by this race to build bigger, more massive models. But this research just proves that incredible, world-changing breakthroughs can come from the complete opposite direction. So if less is more is the secret to cracking these incredibly hard reasoning puzzles, what's next? What other huge AI challenge out there is just waiting to be solved, not by building something bigger, but by thinking smaller, smarter, and way more efficiently? That's the idea I want to leave you with.
You know, in the world of AI, there's this mantra we hear all the time. Bigger is better, right? More data, more compute, more parameters. But what if that's not the whole story? What if that's just wrong sometimes? Today, we are diving into a really fascinating paper that just flips that whole idea on its head. It argues that for some of the hardest logical puzzles out there, less is, believe it or not, more. So let's get into it. Okay, so to really set the stage here, look at this. On one side, you've got the absolute titans of the industry. We're talking models like Grok 4, with a just mind-boggling 1.7 trillion parameters. And then on the other side, we have the model from our source paper, the Tiny Recursive Model, or TRM. And get this, it has just 7 million parameters. I mean, that's not even a rounding error for these giants. It's over 240,000 times smaller. It is the definition of a David versus Goliath showdown. So that brings us right to the heart of the mystery we're going to unravel today. How on earth does a model this tiny, this underdog, manage to solve incredibly complex logical puzzles? Puzzles that can leave even the most powerful trillion-parameter AIs totally stumped. It seems impossible, right? Well, let's find out. All right, section 1, a tiny model's big secret. So what is it? What's the secret sauce here? Well, before we can really appreciate the solution, we first have to get a solid grasp on the problem it was built to tackle. So here's the thing. For all their amazing abilities, large language models, they can really struggle with hard reasoning tasks. Think like super tough Sudoku puzzles or abstract pattern recognition. And the reason why is kind of fundamental to how they work. They generate answers one piece at a time, token by token. It's like they're building a tower of dominoes, and if they put just one domino in the wrong place early on, the whole thing comes crashing down. Now, we have some clever tricks to help, like chain of thought, where you ask the AI to think out loud. And yeah, it can help, but it's super expensive, computationally speaking, and it can still get things wrong. They're basically just clever patches, not a real fix for the underlying problem. Okay, so researchers saw this problem and started thinking there has to be a better way. And this search for alternatives brings us to a really important character in our story, a model called the Hierarchical Reasoning Model, or HRM. Now, this is the direct predecessor to the tiny model we're so interested in today, so it's a key part of the puzzle. The idea behind HRM was actually pretty cool and pretty novel at the time. Instead of building one massive network, they decided to use two smaller networks that would loop over and over, that's the recurse part, to slowly refine an answer. You had one network that was kind of the fast thinker, operating at a high frequency to handle all the nitty-gritty details, and then you had another slow thinker network for the big picture stuff. The whole concept was actually inspired by theories about how different parts of the human brain seem to operate at different speeds. Pretty neat. And yeah, this diagram here really shows you just how involved this whole process was. So the question goes in, right? Then it gets looped through that fast, detail-oriented network multiple times. Then it goes through the slow, big picture network just once. And that whole cycle, it just repeats over and over to chisel away at the problem and refine the answer. It's this really intricate dance between two different systems. Now, I want you to really lock this image of complexity in your mind because it is absolutely crucial for what comes next.
Now, HRM was definitely a big step forward. I mean, it showed some really impressive results. But it wasn't perfect, not by a long shot. When the researchers really started to pop the hood and look at the engine, they found some pretty serious cracks in its whole logical foundation.
And this quote from the paper we're looking at, it's a real bombshell. See, to make this whole complex process work without using a ton of memory and compute power, HRM's entire design depended on a pretty fancy mathematical shortcut. But here's the problem. The authors of our paper discovered that the specific conditions needed for that shortcut to even be mathematically valid, well, HRM wasn't meeting them at all. Okay, so let's break that down just a little. The shortcut is based on something called the Implicit Function Theorem. Now, don't worry, we're not going to do a deep dive into the math here. All you need to know is this one key thing. The theorem only works, it's only valid, if the network's internal state eventually settles down and stops changing. It has to reach a stable, unchanging value. Think of it like a spinning top that eventually finds its balance and just stands still. That's the fixed point mathematicians talk about. It has to stop wobbling.
And here is the absolute kicker. The paper proves that HRM, it never actually reaches that stable fixed point. It just runs a few loops, doesn't wait for the top to stop spinning, and then applies the theorem anyway. It's basically like using a key that doesn't quite fit the lock and just hoping it works. The entire mathematical reason it was supposed to be efficient was, frankly, built on sand.
And, that wasn't even the only problem. Its training process was super inefficient. It had to do 2 full passes through the data just for one little learning step. On top of that, the whole reason for its design was based on these really complicated and, let's be honest, unproven ideas about the brain. And nobody could ever really give a clear answer for why it needed 2 separate networks to begin with. It was just messy. There was a lot of room for improvement here. And this is where our hero finally enters the scene. The tiny recursive model, or TRM. Instead of trying to slat some duct tape on HRM's flaws, the authors just said, forget it. They went back to the drawing board and came up with a fix that is just beautifully simple and elegant.
I mean, just look at this table. It really says everything you need to know. HRM had 2 networks. TRM has just 1. HRM had 27 million parameters. TRM slashes that down to just 7 million. It completely throws out that shaky fixed point theorem and just uses simple, direct backpropagation. The gold standard, robust way we train pretty much all neural networks. And it makes the training process twice as efficient. I mean, look down the list. In every single way, TRM is a massive, dramatic simplification and improvement.
And the core insight that made all this possible was just brilliant. The authors had this aha moment. They realized that HRM's 2 super complicated hierarchical features, they weren't mysterious at all. One was basically just the current best guess for the answer, we can call that Y, and the other one was just the hidden reasoning process, kind of like a mental scratch pad. We'll call that Z. So it's not about some complex hierarchy at all. It's just about separating the final answer from the messy work of figuring it out. And once they had that insight, everything else just clicked into place. All of TRM's beautiful simplifications flow from that one idea. It uses a single network to update both the scratch pad and the final answer. By just doing standard backpropagation through the whole recursive loop, it totally gets rid of the need for that flawed mathematical shortcut. And then, and this is my favorite part, they discovered something incredible. A tiny 2-layer network actually performed better than a bigger 4-layer one. Why? Because the smaller one was less likely to just memorize the training data. It avoided overfitting. It is the ultimate proof that sometimes less is truly more. Okay, so we have a model that's simpler, smaller, and way more elegant from a theoretical standpoint. But that's the big question, right? Does it actually work any better? Well, let's take a look at the data. The results are in, and honestly, they're pretty stunning. First up, let's look at the Sudoku Extreme benchmark, and we're talking about puzzles that are just ridiculously hard. TRM achieved a staggering 87.4% accuracy. Now compare that to its predecessor, HRM, which only got 55%. That is a massive leap. It's not just a little bit better, it's a whole different ballgame. And don't forget, it did all of this with 4 times fewer parameters. Let that sink in. It's smaller, it's more efficient, and it is dramatically more accurate. Yeah. This is the kind of result that makes everyone in the research community sit up and really pay attention. And if you need any more convincing, this chart just drives the point home. This is on the ARC-AGI reasoning benchmark, which is notoriously difficult. And look, TRM, in blue, doesn't just edge out its predecessor, HRM, it also beats a well-known much larger model, Gemini 2.5 Pro. a tiny 7 million parameter model is out-reasoning a state-of-the-art giant. I mean, if that's not proof in the pudding, I don't know what is. So, okay, what does all of this really mean for the future of AI? What are the big picture takeaways here? Is it possible that the path forward isn't just this relentless race to build bigger and bigger and bigger models?
Well, I think this research teaches us a few really powerful lessons. For one, elegant, clever design can absolutely be more powerful than just throwing more compute and more data at a problem. Brute force isn't always the answer. Second, this whole idea of using tiny networks that loop on themselves, this recursive reasoning, seems to be a fantastic way to learn from small datasets without just memorizing them. And maybe, just maybe, this points to a future where we move away from trying to build one giant model to rule them all, and instead move towards using smaller, more efficient, specialized models for specific kinds of tasks.
And that leaves us with a really fascinating question to chew on. As we keep pushing the boundaries of AI, is the answer always going to be a single, giant, do-everything model? Or could the future actually belong to these tiny, mighty, recursive specialists? Almost like an army of them, each one a master of its own little domain. It's a really powerful idea, and it might just change how we think about building intelligent systems.
For years, the story in artificial intelligence has been pretty simple, right? Bigger is always better. More data, more computing power, more and more parameters. But what if that whole story is wrong? What if a tiny, really elegant model could actually run circles around the giants on the problems that matter most? Well, that's the incredible story we're diving into today.
So this is a big question, the one at the very heart of today's explainer. We're going to look at a classic David versus Goliath story, but from the world of AI research, where a really radical new approach is challenging that entire bigger is better philosophy. And when we say Goliath, we absolutely mean it. A cutting-edge model like Grok 4 has a staggering 1.7 trillion parameters. That's the brain power, so to speak, that these models use to understand and generate human language. To put it mildly, these things are just massive.
And that's not some kind of outlier. The dominant trend, this multi-billion-dollar arms race in AI, is all about scaling up. The core belief for years has been that if you just make the model bigger and you just keep feeding it more and more of the internet, it will eventually get smarter and be able to solve any problem you throw at it. But it turns out that's not quite what's been happening.
What's really fascinating here is the clear divide you see. These large language models are absolutely phenomenal at tasks that are based on patterns they've seen in their training data. Writing a poem, summarizing an article. But the moment you give them a problem that requires pure structured reasoning, like a really hard Sudoku puzzle, they fall apart. They can guess based on what they've seen before, but they can't actually think their way through a new problem from scratch.
And this isn't just a minor quirk, This points to a pretty fundamental weakness. There are these benchmarks designed to test for genuine artificial intelligence, like ARC-AGI, and they consistently stump these giant models. Even on puzzles that seem simple to us, the biggest AIs often fail and fail spectacularly, revealing this big crack in their armor. And this is where our story really begins.
So, faced with this obvious reasoning gap, some researchers decided to just step off the bigger is better treadmill completely. They came up with a totally different approach, one inspired not by massive scale, but by a more structured, almost biological idea of what it means to think.
They called it the hierarchical reasoning model, or HRM for short. Now, instead of one giant network, it used two small specialized networks. The idea was that one network, FL, would handle the low-level thinking at a really high frequency, while the other one, FH, would handle the high-level planning, but at a lower frequency. It was this fascinating concept, and it showed some real promise on those hard reasoning puzzles. But the process itself was, well, it was complicated. It involved this really intricate dance between the two networks. And to make the whole thing work efficiently and save memory, it had to rely on this clever but really complex mathematical shortcut to learn from its mistakes. A trick that, as we're about to see, had a pretty major downside.
So here's the crucial point. HRM was a clever first step, for sure, but it was kind of built on a shaky foundation. As the researchers who came after them pointed out, it was leaning really heavily on these complex biological analogies and some pretty dense mathematical theorems that might not even apply in this situation. So yeah, it worked better than the giants, but it was way too complicated and totally ripe for a revolution.
And this is where the real breakthrough happens. Enter our story's hero, the Tiny Recursive Model, or TRM. The researchers behind it looked at everything HRM was doing, and they asked a really simple question. Can we get all of the benefits, but with none of the complexity?
And the answer was a resounding yes. TRM just throws out the whole two-network system, the confusing biological arguments, and all the complex math. It uses just one single tiny network. Its core idea is just beautiful in its simplicity. Take a guess at the answer, and then use that very same network over and over again to think about its own guess and make it better.
I mean, just look at the difference. Compared to that complicated dance HRM was doing, TRM's process is so incredibly elegant. It has a thought vector, let's just call it Z, and an answer vector, Y. And it just loops, using its thought process to refine its answer again and again. It's letting the model literally think about the problem, step by step.
And this is the absolute breakthrough. Instead of that complicated shortcut that HRM was using, TRM does something much, much more powerful. It learns from its entire chain of reasoning. Think of it like a student showing all their work on a math problem. By looking at every single step, the teacher, or in this case the algorithm, can give much better, more precise feedback. That complete picture was the secret sauce.
Okay, so we've got a simpler, more elegant model. That's great, but does it actually work any better? Let's put this tiny model up against the giants and its predecessor HRM and see what happens. The results are, well, they're pretty shocking. This right here is the knockout punch. On a dataset of extremely difficult Sudoku puzzles, a massive 67 billion parameter LLM gets a flat 0%. It can't solve a single one. HRM, the complicated predecessor, does okay, pretty well actually, at 55%. But our tiny, simple TRM, it achieves an astonishing 87% accuracy. It's not even a competition.
So why? Why is it so much better? Well, this wasn't just luck, it was superior engineering. The paper actually breaks down the impact of each design choice, switching to full backpropagation, learning from the whole thought process. That alone gave them a massive 31% boost. Using a single network instead of two added another 5%. And get this, making the network smaller with just 2 layers instead of 4 actually improved accuracy by another 8%. Every single simplification made the model stronger.
Let's just pause for a second and appreciate the difference in scale here. The LLMs we're talking about have billions, sometimes trillions of parameters. TRM achieves these incredible results with just 7 million. That is less than 0.01% of the size of the larger models. It's the very definition of working smarter, not harder.
And this isn't some one-trick pony. The exact same pattern holds true across other really tough reasoning tasks. On hard mazes and that difficult ARC-AGI benchmark, TRM consistently outperforms both the much, much larger LLMs and its more complicated predecessor, HERM. This is a fundamentally better approach for a whole class of problems.
So, what have we learned from this incredible David versus Goliath story? What's the moral here for the future of AI development?
Well, what's the big takeaway from all this? First off, brute force is not the only answer. This recursive approach lets even a tiny model think deeply, iterating on its solution in a way that the giant models just can't. A clever algorithm can be way more powerful than a massive one. And it turns out, a simpler, more elegant design is often the most effective. But maybe the most exciting part? This opens the door for incredibly powerful AI that doesn't need a huge data center. It could run on your phone, in your car, on any small, everyday device.
The success of TRM really proves that the AI arms race isn't just about size anymore. It's about ingenuity. And it forces us to ask a really exciting question. What other giant-sized problems in science, logic, and reasoning are out there, just waiting for a tiny, clever model to come along and solve them? The game, it seems, has completely changed.